Hi class, welcome to part 1 lecture on the thermodynamic principles of refrigeration using CoolProp software. So today we'll look into some basic principles of thermo as related to or as is relevant to the refrigeration course. Thermodynamics essentially is the science that deals with the principles governing transformation of energy and also transfer of energy. Okay. And the main concepts would include energy in the form of heat, work, internal energy, enthalpy, etc. This will help us define a framework to understand the capacity and performance and the efficiency of different types of systems we will deal with later on. Okay, so things like cooling capacity, coefficient of performance, energy efficiency ratio, things like that are coming basically from the thermodynamic principles. Now, essentially, there are four laws of thermodynamics that we'll learn in this course. Two of them we'll brush upon in this particular lecture, which will be the zeroth law and the first law. Okay. The later two laws are more dependent on the term called entropy, which is also a form of energy, um, if you will. It will be discussed in the subsequent lectures. Okay. And predominantly the nature of these lectures will be trying to understand the principles by actually calculating the values of different properties and systems using CoolProp. All right. So what is the first concept here? The first thing to learn here would be about a thermodynamic system. And for such a system, what defines such a system is a small region. It doesn't have to be small, but a region or a quantity of matter that is enclosed by a boundary such that it is separated from its surroundings. Okay. Now this boundary could be real or imaginary, and this boundary could be fixed or movable. Okay. So if you consider a piston cylinder system, okay, so the piston is movable in this direction. So you could have a system defined inside the cylinder, and that could move according to the position of the piston. Okay, so this is also a thermodynamic system, even though the boundary is moving. So it could be fixed or movable. Another thing to note here is broadly we classify the systems into three categories: open, closed, and isolated system. Open and closed systems are readily available in nature or in your surroundings. They're very common. Okay. Um, a coffee cup, a hot coffee cup, and if you draw a boundary around the cup like this, there is water vapor and other chemicals leaving the boundary, right? You can smell a coffee, means there are coffee flavor leaving the cup. There's probably some milk particles leaving the cup too. So a lot of chemicals leaving the cup, water vapor leaving the cup. So there is a lot of mass transfer across the boundary. And if you leave the coffee cup on the table for a while, it'll cool down. So there is energy leaving the cup, that it's becoming colder. Okay, so such a system is called open system because there's transfer of mass and energy across the system boundary. Now, if you have a bottle of water and it's sealed really tight, and if you draw a system boundary like this, and then the thermodynamic system inside um, can be considered closed to the transfer of mass. Okay, it's close to the transfer of mass, but there is exchange of energy possible. You can cool the water by putting in a fridge, or heat the water by leaving it outside in the sun or in a hot room. Um, so there is transfer of energy, but essentially the mass or the uh, molecules inside is trapped and it's closed. Okay, so there's no matter transfer. So that such a system is called a closed system. Um, then there's a third system, which is basically an idealized system. It doesn't really occur in real life. It's not common, and that will be the isolated system. So there is no matter, no energy that is going across the boundary. It is hard to create or find such a system. The one that comes close to such a system under certain conditions is a vacuum insulated bottle. It sometimes you call it as a thermos bottle. Okay, so a thermos bottle has vacuum insulation. Okay, so such an insulation will reduce the heat transfer significantly. Um, but you know for a fact that you cannot store hot water or cold liquid inside a thermos indefinitely. So usually when you look at the advertisements, it will say 12 to 18 or 24 hours of storage. Okay. So basically, I personally have done some experiments in the past. They usually lose roughly about 1 watts um, per day. Okay. Sorry, not per day. 1 watts of power they lose. So um, at any given point, if the water stored in it is at 70 degrees or 80 degrees C or so. So it's not 0 watts. So there is energy loss through this. But if you're considering only a short period of time, you can say this is a uh, closed system, plus there is no mass transfer, so it's an isolated system. Okay, but it is usually used for idealizations, for deriving equations, for certain practical, not practical, certain theoretical considerations for solving certain specialized scenarios. Okay, so those are the three systems. And sometimes the open system is also called as control volumes, especially in fluid mechanics. Okay, in thermodynamics, it's usually known as an open system, but in fluid mechanics, we call it mostly as a control volume. Closed systems are also known as control mass. All right, so that's our first thermodynamic concept, the concept of having a system. Now, the next concept is the state of the system. Okay, what state is the system in? If you have a bottle of water, what is its state? What temperature is it at currently? So that's what you mean by state. Okay, like what are the properties of that system? So a state has to be defined concurrently with the definition of thermodynamic property. Okay, so a state is defined as a condition of a thermodynamic system as it's described by its properties. So to describe a state, we need to know what is a property. Thermodynamic properties are measurable or calculable physical quantities. Okay, examples would be pressure. Pressure is measurable. Temperature. Okay, or you can calculate the physical quantity. An example would be specific volume. Okay, um, I wouldn't say specific volume. Yeah, specific volume, and then the other quantity would be density. Okay, another quantity would be calculable quantity would be enthalpy, things like that. Okay, Um, so these describe the state of the thermodynamic system. And these properties, thermodynamic properties, are also called state functions. Okay. The meaning of that statement is the values of these properties are only dependent on the current state. It does not matter how they reach their current state. So if you have a bottle of water at state 1, which is the current state, okay, now this bottle would have been in your car and it came to this state from a high temperature state. Let's say it was 38 degree or 39 degrees C, and the current state is 18 degrees C. It could have also been come from a fridge. It used to be maybe 4 degrees C, and it reached 18 degrees C right now. It doesn't matter how it got to this state. All that matters is it is at this state right now. So properties are state functions. Okay, we'll look into that briefly in the next slide. Another thing to note about properties is they are classified into different types, and one of the ways to classify them is intensive versus extensive property. Okay, so let's look at the bottle of water again. So let's say there is a bottle of water, and the whole bottle is at one particular temperature. Okay, and then you take a smaller volume inside the bottle and look at the temperature of that smaller volume. That's also at a temperature T. So if you have properties that doesn't depend on the size or volume or mass, then such properties are called intensive properties, independent of system size or mass. Examples would be pressure, temperature, density, specific volume, specific enthalpy, etc. So all of those properties, if you take one for the bulk fluid and then take a smaller volume or compare between two volumes inside this, they'll be the same. And then there are properties like volume, mass, entropy, internal energy, etc. that depends on the size or the volume or mass. And by this, what we are meaning is it depends on the number of molecules. Okay. So if you select a smaller volume here and say, what is the mass of this compared to the mass of another one, the mass will be different, right? So it is dependent on the number of molecules. The more the number of molecules, the weight or the mass is different. The same thing goes for the total entropy, internal energy, etc. Okay. So such properties are called extensive properties. Volume of a smaller uh, system here versus the larger system, that'll be different, right? So that's the main classification. The other classification was whether it is measurable or calculable. Okay, some are directly measurable, some cannot be measured. They are calculated based on other measurements. Now, how many properties do we need to define a state? For a simple compressible system, like a simple gas, okay, let's say air or nitrogen or a simple gas, then all you need is two independent properties. Okay, two independent energy properties are sufficient to define the state. So examples would be pressure and temperature, or pressure and specific volume, and we'll get into these properties soon. Temperature and density. Okay, pressure and density. Any of those will describe the property of the system or that particular state. Okay. The thing that you have to be careful though is they have to be independent. Now, if instead of air you had a mixture of liquid and vapor, for example, of water. Okay, in this case, you have to be careful. You can use pressure, volume, pressure, temperature, density, pressure, density, all of those are okay, but you cannot use pressure and temperature. Why? If you remember the phase diagram of water, and if you remember the pressure temperature relationship, right? At saturation, pressure is a function of temperature, and that function was similar or could be derived from the Clapeyron equation. Okay, so essentially, you could say pressure is somewhat of an exponential function of temperature, okay, based on the Clapeyron equation. So pressure is not independent of temperature for two-phase regions or two-phase mixtures in equilibrium. For single-phase gases, pressure and temperature are, you can vary them independently. So what do I mean by independent? So you cannot change pressure by keeping temperature constant in this scenario. Okay, if you change pressure, the temperature will increase accordingly based on this equation along this line. But for a gas, you know PV equal to nRT, right? If it's ideal gas. So you can change pressure and keep temperature constant as long as you vary these other things accordingly. Okay, so same thing with temperature. You can change temperature and keep pressure constant. So you can change them independently. You cannot do that when they are talking about a two-phase system. So for a simple compressible system, two independent intensive properties are sufficient to define the thermodynamic state. Again, it has to be intensive property. You cannot define the state using the total mass, for example. Okay, but density will work. Density is mass per volume. You can use that to define this because it's an intensive property. You cannot use volume, but you can use specific volume, which is volume divided by mass, because that's an intensive property. Okay, all right. Now, this is touching upon the state function that we discussed here. So just to drive the point home further, consider that you are in state 5. Okay, your system is at state 5. You could have gotten there um, from state 1, 2, 3, or 4. So 1 to 5 is isobaric, means P equal to constant. Okay, 2 to 5 is isothermal. By the way, this is a pressure volume chart. Okay, pressure volume diagram. So isothermal lines will be like this, and you can use PV equal to nRT to figure out the curve of this line. Okay, so isothermal means T is constant, so PV equal to constant. Then you'll get a curve like this. Okay, then adiabatic means there is no heat transfer. Okay, um, so that will give you another line like this. Isochoric means volume is constant. Okay, so you could compress from any of these solutions, any of these states, and you compress your gas to the final state 5. And the properties P5, E5, T5, this is specific volume. All of these, it doesn't matter how you got there. Okay, and using these properties, you can calculate the other properties for the system: enthalpy, entropy, internal energy, etc. Okay, all of them, it doesn't matter how you got there. So that's why properties are called state functions. They only depend on the state. Okay. Now, this slide gives you a bunch of properties that will be useful for in this course. And again, like we discussed before, there are two ways of classifying the properties. One is properties that are measured directly, they're called primary properties, and properties that are measured indirectly or calculated based on the primary properties, they're called derived properties. The typical measured properties are pressure, temperature, volume, and mass. Okay. Now everything else is a combination of these, or not exactly a combination, but derived based on these or other measurements. Okay. Um, Now you can use a pressure sensor to measure pressure, temperature sensor to measure temperature. You could use dimensions to measure volume. You could use a weighing scale to measure mass. Uh, but to measure density, you have to use the mass measurement and the volume measurement. And to measure internal energy, you have to measure energy, which is indirectly measured by measuring temperature, pressure, volume, etc. Okay, so that's the distinction between primary and derived properties. There is also some properties categorized as intensive versus extensive here. And one thing you should notice, internal energy is extensive, but specific internal energy is intensive. Okay, volume is extensive, but specific volume is intensive. So what is the difference? Whenever we say something is specific, it becomes intensive. So if you are dividing something, some property, and estimating it per mass, okay, or per volume, or per mole, okay, per mass, per volume, per mole, then those properties become specific, intensive, okay. And typically when you're calculating something per mass, um, you call such properties as specific property. Okay, because it's per mass of that substance, so it's independent of the size because you're already dividing per mass. So you could see whenever there's a per kilogram, um, it is considered as a specific value, and also it is intensive. Okay. um, you could also have something per mole, and it will also be intensive. All right. Okay, so let's introduce the first law of thermodynamics, which is basically the zeroth law. Okay. um, so zeroth law is important because it helps us with temperature measurements. Okay, so what does this mean? This basically, there's a couple of things you have to take away from this law. One is the concept of thermal equilibrium. Okay, so when two bodies are next to each other and they have different energies, there is energy transfer from one body to the other. And at some point, that transfer ceases and it becomes zero. At that point, the temperature of both these bodies are the same. And this concept is called thermal equilibrium. Okay, so at thermal equilibrium, there is no thermal transfer between the two bodies. Okay, and it doesn't have, and they don't have to be in contact even. Okay, so if you have to measure the temperature of a body, okay, and you put a thermometer there, okay, so you'll see the reading on the thermometer go up, 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 and then there's no change at some point. So we assume that we reached thermal equilibrium, and right now the thermometer and the body that you're trying to measure the temperature, they are at the same temperature. So the temperature measured by the thermometer is the correct temperature of the body that you're measuring. There are some nuances here. You have to, of course, account for airflow. that might give you a temperature value that's slightly lower, but we won't go into those details. But if there's no other heat transfer effect going, then um, then this law is the definition of this law can be explained by this example. Another thing to note here is if there are two bodies and you measured both of them with a thermometer and they're both reading temperature T, then there's no heat transfer between the two bodies. Okay, so if two bodies are in thermal equilibrium with a third body, then they are also in thermal equilibrium with each other. Okay. All right, so it's just um, further improving on the definition of temperature and how it relates to transfer of heat. The next property of importance is the specific volume, and we know that it's an intensive property. It is basically nothing but the reciprocal of density. Okay, there's nothing magical here, but I think we will start with trying to find finding the specific volumes of different fluids using Coolprop. Okay, and the densities unit is kilogram per meter cube. The reciprocal of that, which is meter cube per kilogram, is the units for specific volume. All right. One other thing to note here is Coolprop does not have a property for specific volume. Instead, you have to calculate density using the D property and then take the inverse of that to estimate the specific volume. All right, let's open Coolprop at this point and look at specific volume of different gases, vapors, and liquids, and try to get some understanding on the range of numbers that we will see. All right, here I have water, helium, air, and nitrogen at different temperatures. Um, and I have also chosen certain pressures to calculate the density and then calculate the specific volume. So first thing, let's look at gases like helium. So I'm choosing a temperature 10, and then I'm choosing a pressure that is atmospheric pressure in pascals. Then using the props SI function, you can easily calculate D for the two variables temperature and pressure. Okay, this 273.15 is converting the degree C to Kelvin, and it's giving the value in kilogram per meter cube. So the specific volume is 5.8, which is the inverse of this number. Okay, and as we increase the temperature, we can see that the density is decreasing and the specific volume is increasing, which makes sense. Things expand as you heat, so the density of gases typically decrease as the temperature increases, and the specific volume is just the opposite. It increases as the temperature increases. Okay, you could see that here. And similar things are done for air and nitrogen. Okay, and you can see some of them are much higher than the others. For example, helium seems to have much higher specific volume. What that means is for the same, so if you have 1 gram of helium vapor, it will have several times, 5 to 6 times the volume of air. Okay, because it has a much higher specific volume. Now, what about water and its two phases, liquid and gas? Now, what I've done here is I tried to calculate the density of water in liquid and gaseous phase. Um, Instead of using the quality function, I used the pressure and temperature. But what pressure did I use to get a liquid phase, and what pressure did I use to get a gas phase? So what I did is I picked a point somewhere in here. Okay, assume this was 25 degrees C. So this is somewhere around 3169.93 Pascal. So this is the two-phase region, and that's the saturation pressure. Okay, So I calculated the saturation pressure using the process I function for qualities 1. Now, if I go 1 pascal lower, what happens? So if I go slightly lower than this, I'm in the gas phase or vapor phase. Okay. If I go 1 pascal above in pressure, I'm in the liquid phase. So that's what I've done here. So I removed 1 pascal and it's a smaller pressure than this. Then I use this temperature and this pressure to calculate the density of the vapor phase. I added 1 pascal to calculate the density of the liquid phase. Okay. I could have done it differently, but I chose to do it this way. So what did we get? The density of the um, gas phase is so low that the meter cube per kilogram or the specific volume is huge for water vapor compared to other gases. Um, and the density of the liquid is of course close to the 1000 kilogram per meter cube of water, and the um, specific volume is really low because of that. Did the same thing for R134A for its two-phase mixture, and you can see the density differences and the specific volume differences here. Okay, so use this uh, tab to brush up on your skills on how to calculate specific volume and also trying to understand the two-phase region. Okay, all right. The next property that is of importance is quality, and you will deal with this quite a lot because refrigeration involves a lot of two-phase calculations. Okay, because there is evaporative cooling. Remember, um, so evaporative cooling means there is change of phase, and refrigeration always involves a lot of change of phase. So a property that is related to the change of phase is quality. So what is quality? Um, it is the portion or the proportion of vapor in a two-phase mixture. So quality could also be called as vapor quality. Okay, so think of quality as vapor quality. So vapor quality means what is the quality or amount of vapor in your mixture. A high quality mixture means there's a lot of vapor. A low quality mixture means there is very little vapor, it's mostly liquid. Okay, and the actual definition is the mass fraction of vapor. So the mass of vapor, it's not the volume of vapor, it's the mass of vapor in the liquid vapor mixture. So it's typically denoted by the variable x, but in cool-prop the variable that they use mostly is q. Do not confuse this with heat, which is the thermodynamic notation commonly used. Okay, so what is x or q? It's the mass of vapor divided by the total mass, which is mass of vapor plus mass of liquid. And let's say you have a system, okay, and you have a quality Q, okay, and you have vapor phase and liquid phase, liquid and vapor. Let's say you have certain specific properties. You remember the properties that had per kg or per mass. So suppose you had a property like that, a specific internal energy or a specific um, volume even. So you can have that property for liquid and for vapor. So let's call it Y liquid and Y vapor. The question is, how do you use Q to figure out what is the property of the whole mixture, or what is the actual property of the state Y? Y mixture equal to Y, for example. How is that related to Y liquid and Y vapor and Q or X? So since this is the specific property per mass, a mass weighted average is all you need to calculate this. Okay. So what does that mean? Um, so if you have Y liquid, then what you need to do is what is the ratio of mass of liquid in this, and what is the ratio of mass of vapor in this, and then multiply them with their corresponding values. So in that case, Y is equal to the mass of vapor, or the vapor fraction, is X. So X times the property of vapor, Y vapor. And what is the mass fraction of liquid? It will be 1 minus X. 1 minus X times the property of liquid. Okay, so that will give you the property of the mixture, which is this equation. And using this equation, you can derive this, and using this, you can derive this. So X can be determined based on the other three properties, the mixture's property versus that of the individual um, phases. Okay. All right. Now, to describe the state of the system, you could describe it using this Y value and temperature, Y value and pressure, Y value and any other intensive property, but you cannot describe the state of the system using T and P, as we had discussed before, because T and P are, for a two-phase system, T and P are not independent. But any of these specific property with another specific property or another property like temperature, you'll be able to describe the state of the system and calculate other properties. Okay. All right, so let's look into this using the CoolProp Excel. Go to the Quality tab, and here we have calculated the quality of different two-phase mixture scenarios, one for water and one for R134A, which is a refrigerant. Okay, so what we have done here is we use the temperature, calculate the saturation pressure, and then calculated the inverse of density for vapor and inverse of density for liquid, which is basically the specific volumes, okay, of gas and liquid, and then calculated a um, a mixture value which will be in between these two. Okay, so what we are doing here is this is a Y liquid, Y gas that we just looked at, and Y liquid here, this one, and this is the Y mixture. Okay, so the Y mixture property has to be between that of Y gas and Y liquid. Okay, this is the maximum volume you can have when it's fully gas. This is the minimum volume you can have when it's fully liquid, and anything in between means it's a mixture. Okay, so if you put some value in here, what is the corresponding Q value? So you can calculate that using the process I function. So for a given temperature and the um, the Y value, you can calculate another property, which is Q. So in this case, the state is determined by temperature and specific volume, okay, and we are using that to calculate Q using props SI. All right, and the reason why we did this is to make sure that we don't put any number outside of this. So if I put a value too high, it should give me an error. This means the Q is not between 0 and 1. So I have to put a value between these two to make sure that I get some meaningful result. Okay, so it's giving us a value between 0 and 1. Now you could calculate the same thing using this formula. without using the props SI function. You could use this formula. Okay, you have Y liquid, and Y vapor. Then you can use those three things to calculate X, and they match exactly. Okay, so you change these numbers and test it, and you can see that every single time they match. Okay, and you can replace this with another specific property, and you should be able to get the same type of results. Okay, you can replace this with specific internal energy, for example. You should be able to get the same type of results. All right, so that's about quality. The next property that we should look at is internal energy. Internal energy, as you can guess from the name itself, it is the total energy contained within a system, and it's inside the system. So it's inside due to all the microscopic motions and interactions of its molecules. Okay, so if you look at inside, if you imagine a imaginary microscope where you can actually look inside a substance at any given temperature, as you keep going down and magnifying as you go down, um, you will be able to see molecules moving around, some of them vibrating, some of them spinning, some of them have bonds within themselves, and like ionic bonds, etc., between atoms, covalent bonds, etc., right? So they have a force of attraction within their molecules, and maybe two different molecules will also have attraction. There will be van der Waals forces. Um, there could be hydrogen bonds, etc., right? So there is a lot of intermolecular and intramolecular forces. There is a lot of microscopic motion, and all of this energy can be split into two different groups. One is due to the motion, which is translation, rotation, and vibration motion. The other is all the forces, okay, intermolecular and intramolecular forces. Um, so in solids, there is not a lot of motion. Okay, most of the energy is stored in the intermolecular forces, so they are so tightly packed. Most of the energy is in the bonds that hold them together. Okay, so as you heat the solid, if you heat it, the kinetic energy modes start becoming important, and they start moving a little bit, and some of these bonds break between the molecules, and they are able to move a little bit and become liquids. Okay, the solids melt. So now you have both potential and kinetic energy, both intermolecular and kinetic energy. And as you heat it further, you become a gas, and it's mostly kinetic energy um, due to molecular motion and less intermolecular forces. So if you were to look at a comparison of internal energy, the solids would be lower than liquids, and the liquids will be lower than the gases. Okay, so as you heat, the internal energy takes them through different phases. You probably have never seen that when you heat vapor, the water uh, condenses, right? Or when you heat the water doesn't become ice. It's the opposite. So most of the energy um, is in the gas phase. The internal energy of a gas is usually higher, a lot higher than the corresponding uh, liquid or solid phases. And in solids and liquids, internal energy changes mainly with temperature. Okay, in all scenarios, internal energy changes mainly energy is mainly a function of temperature. Okay, you might wonder, why can I not increase the internal energy of molecules by adding pressure? Right? If I add pressure, I'm putting a lot of work on the fluid. Doesn't it cause an increase in either these kinetic energy or potential energy when you add a lot of pressure? The answer is no in most scenarios. Um, for solids and liquids, there's hardly any volume change when you add pressure. In gases, even if there is a lot of volume change, um, the effect is zero for ideal gases, but it also is very negligible in real gases. Okay, it has some effect. Pressure has some effect in real gases, but it's mostly negligible, and we'll find that out using coolprop. Okay, before we use coolprop, the other question is, um, so what is the reference point for internal energy? Okay, like if you look at water at some temperature T, it might have an internal energy value of, you know, I don't know, let's pick a number, 2000 kilojoules or something. Okay. Um, how did how do we know that? How do we know water has this much energy inside? Okay, it's just sitting there at that temperature. How do we know it has that much energy? Actual actual answer is we don't know. Okay, it's just a random number that we're picking based off of a reference. We have assumed that some other temperature T naught internal energy is zero. Okay, so based off of that, we know that if we add heat to water and we know how much we are adding, that creates a delta energy. Okay, so the delta internal energy is all what we are um, interested in. And different people or different agencies choose the T naught and the internal energy baseline value differently. Okay, sometimes in some cases you could have negative internal energy. Okay, um, and that's because you have chosen your 0 point at a high enough temperature that at a lower temperature the internal energy is actually negative. Okay, so this is an important thing to know. So you could use coolprop and you'll get an internal energy value of this, and you can use some other software and you could get a different internal energy value, for example, right? So but they both will work correctly when you're looking for a difference between two states. All right. And in case of water, at least in coolprop, the internal energy is defined to be zero at saturated liquid state of 0.01. Okay. All right. So before we go into coolprop, let's try to see what we should look into using coolprop. Um, what are the answers we are looking for? We are looking for what are some of the internal energies of some common substances. Um, when does a substance have zero internal energy? At reference point, thermodynamic reference point. How does internal energy vary with temperature at constant pressure and vice versa? How does internal energy of ideal gas differ from real gases? How does the energy of liquid phase differ from the gas phase at saturation? All right. Having said that, let's start looking into the Excel file. First, let's go into this tab where there's a bunch of fluids that you can calculate the internal energy. One thing I forgot to mention is the internal energy notation typically in thermodynamics is U, and um, the specific internal energy notation is U. So this specific internal energy is U over M, where M is the mass. Okay, so U, the units is joules per kilogram. In cool prop, the symbol is capital U, but what they mean by that is small u, okay? It's actually joules per kilogram, right? There's plenty of ways you can get confused here, but let's try not to. Okay, so here, like I mentioned before, you could see a lot of values at 25 degrees C, okay? A lot of internal energy of different gases. All you're providing them is a temperature and a pressure, and typically the pressure shouldn't matter much. Um, let's double this pressure and see how that changes. So it is not a lot of change, you know. If you've looked at this particular or these two numbers, we have changed the pressure significantly, and it didn't change those numbers significantly. Okay, it's a slight change there. And especially it's true if it is an ideal gas. And we'll look into that in more detail soon. Next, let's go to the reference state tab. Here you have different fluids, and they have an internal energy close to zero at these particular temperatures. Okay, for water it's close to 0.01. For R600A it's somewhere close to minus 96 C, and for acetone it seems to be close to its boiling point, which is 56 degrees C. All right, so that's examples of some reference points. Next, let's look into the effect of temperature and pressure on internal energy, and let's try to prove that only temperature matters in most scenario. All right, so let's look at constant temperature condition. So imagine a system going from state 1 to state 2. Okay, so T1 is equal to T2. P1 equal to P2 minus delta, or P2 is basically higher than P1. Okay, that delta P is 3000 Pascal. And we have water as a liquid, water as a vapor, R600 as a liquid, R600 as a vapor, and a lot of gases. Okay, and you can see the P1 and P2 are calculated based on the saturation pressure for these two-phase liquids, and then they are calculated for liquid state in one scenario and calculated for the gas state in the other scenario. And then you have the two different internal energies. Okay, and what we're looking for is how is U2 changing, U2 minus U1, is that zero or not? Okay, for pure liquids it's almost zero, it's 0% change. And for gases that are very close to ideal gases, also it's almost 0%. But when you have some things that are closer to real gases, when they are closer to phase change or they have a larger molecule size, they do have an effect. So as the pressure increases, internal energy decreases slightly. Okay, for such scenarios, what that means is the molecules are getting closer, and the intermolecular forces are getting significant or slightly significant. You're still looking at very small percentage value. Okay, so pressure does have some effect on real gases. In terms of temperature, now consider the scenario where it's all about temperature. Okay, so you have two systems. P1 is equal to P2. It's the same system going from one state to the other. What is the difference? T1 is equal to T2 minus delta, and that delta is 30 degrees C. In that scenario, for liquids, there's a big change in internal energy. For all of the things, there is significant change in U. So U is clearly a function of T. And based on this, U is not a function of pressure. Okay, even though there is some effect for real gases, it is safe to say that U is generally a function of T. Now, how does the internal energy of the gas um, compare with that of the liquid? Suppose you have a mixture of liquid and vapor. Which one will have higher internal energy? Based on what we have discussed before, the vapor should have a higher internal energy, right? And you can see those numbers here. So water, when it's vapor quality of 1, you can use the quality and pressure. So we are using pressure and quality. So U is a function of pressure and quality to calculate. U is not a function of pressure and quality. You're just estimating U based on pressure and quality. Okay, because that's how you calculate the state. So using that, the value is this for vapor, and for Q equals 0, you get this, which is for liquid. And you can also estimate it for any other quality, and it will be a value in between. Okay, and you can check whether that is correct using our formula of mass weighted average. Okay, and that's working. All right. So that's some of the questions answered about the internal energy. So when you think about internal energy, think about all the microscopic molecular motions, and when somebody says internal energy, immediately think of temperature, okay, because it's primarily related to temperature. Okay, so regardless of the pressure, if they didn't tell you what pressure it is, you should be able to estimate it based on temperature. But if it is in a two-phase region, you definitely need to know the quality, okay, because it is very important to know the quality. So you could have a 0 quality and a low number, and a quality of 1 and a high number. Okay, so if it's a two-phase region, it is definitely dependent on whether it's in more of a vapor or more of a liquid. Okay, all right. The next thing to know is about heat and work. Heat and work are different forms of energy, and it describes energy transfers that occur between a system and surroundings due to temperature differences. Okay, so Q and W primarily based on temperature differences. There are other types of works which are based on um, electrical work or shaft work, things like that. But in this lecture, we are mostly focused on work due to temperature differences. Both are path functions. So what does that mean? So if you have, let's look at the same PV diagram that we looked at before, and you have, let's say, a point here and another point here, and you want to go from here to here, you can go in an, for example, an isothermal way, or you can go from 2 to 1 in an isochoric and an isobaric way. Okay, so there is a path A and a path B. So the amount of Q and amount of W goes that one takes through path A and path B. So QA not equal to QB, WA not equal to WB. So A and B depend, and Q and W depend on the path that you're taking from going from state 2 to state 1. So such functions are path functions, and heat and work are very path dependent. Okay, so there is no direct equation for heat where you can say it's always this function. No, it is very dependent on the path, how you get there. Okay. Um, and typically, one thing to note about tea is it occurs spontaneously from a higher temperature to a lower temperature. And when the temperatures match, they reach a thermal equilibrium. The sign convention is if if the heat is going inside a system, okay, then it's positive. Heat leaving the system is negative, okay, and it's the opposite for work. If there is work done at the boundary, something is pushing it down, then that work is negative. Like if this is pushing it out, okay, work is going, if you're pushing a piston out at the boundary, then the work is positive, okay. All right. So based on the definition of heat and work, let's jump into the first law of thermodynamics. So we have looked into zeroth law before, which is basically a statement on thermal equilibrium and temperature measurements. This law is basically about conservation of energy. Okay, so it can be stated in different ways, but in this case, we are interested in a thermodynamic system. So the energy cannot be created or destroyed statement becomes something like this. So if you put in an amount of energy that is Q, it just gets transformed into internal energy and work. Okay, so energy is not created or destroyed, it just gets transformed into internal energy and work. Okay, so that's how you account for the total energy. Heat added to the system, change in the system's internal energy, which basically means temperature change, right? Internal energy is a function of temperature primarily, and then work done by the system, okay, on the surroundings. And work done is typically, you would have learned from your previous experience that most of this work is pressure volume work. Okay, all right. The next concept to know, once we have learned about the first law, internal energy, um, is the enthalpy. It's hard to describe enthalpy as a property, um, because internal energy, it's easy to explain. It's the sum of kinetic energy and potential energy of the molecules. In terms of thermodynamic, in terms of enthalpy, it's internal energy plus the pressure and volume of the system in its current state. Okay, what is it? If you has the pressure and volume, then multiply pressure with volume in its current state. So add the internal energy, which we can understand that the molecules are moving. Then we also need to multiply pressure and volume. And if you look at the units of pressure and the units of volume, if you multiply them, you basically get the units of energy. Okay, Pascal times, you can do this as an exercise. Pascal times meter cube. Pascal is newtons per meter square, right? So newtons per meter square times meter cube, it gives Newton meter, which is the units of joules. Okay, so pressure volume is basically some type of energy. It's not very intuitive how that is the total energy of that system. But if you have to think of it this way. So suppose you have a system sitting there with pressure and volume of a certain value, internal energy U, then H is the energy that can be imagined to be required to create the system. So you created the system from zero energy, so you added U energy to create the internal energy, but then you also have to push and create this volume against a pressure, outside pressure of P. So it's the total energy that somebody had to expend to create the system. Okay, so that's one way of looking at it. All right, so if somebody had to create a system with internal energy U, they had to spend more energy than U, and that extra energy is the PV energy. Okay, so U plus PV is that extra energy that somebody had spent, and then you name that and everything together as enthalpy. Okay. Another thing to note here is for processes at constant pressure, change in enthalpy corresponds directly to heat transfer. So Q is same as H if P equal to constant. Okay, you remember the previous equation where Q is delta U plus W. If P equal to constant, then delta H is equal to delta U plus W. Okay, and in such scenario, you typically that W is P delta V because P is constant, and you get that equation that you've learned before um, in your previous classes probably. All right. And the other thing to note now is the um, importance of enthalpy and the latent heat. You know, the latent heat is the amount of energy that is absorbed or released during phase change, right? So, you know, like when water is boiling, for example, how much energy is needed to boil, let's say, X kilogram of water, right? So that E over X is basically the latent heat for boiling at that temperature at 100 degrees C, right? So how is enthalpy related to this latent heat L, right? Um, let's look into that. One thing to note here is phase change typically happens at constant temperature and pressure, okay? Um, and examples are melting, boiling, sublimation, etc. So when such phase change is happening at constant temperature and pressure, what do we know? Enthalpy directly corresponds to heat transfer. So change in heat is equivalent to change in enthalpy. So the Q, whatever that you're adding, in this case the latent heat, is, or if you can write it as mass times L, the total energy, right, is same as the change in enthalpy. All right. So I think I should have put a mass here. I should have put a mass here. MFG is ml and HFG is same as L. Okay, so change in internal enthalpy is same as the latent heat at phase change, right? And everything comes because it's defined at constant pressure. All right, so we looked at heat and work, we looked at first law of thermodynamics, we looked at enthalpy as a function of internal energy and pressure volume work. We looked at enthalpy and latent heat. Now let's start using CoolProp to answer some of the questions. First, using CoolProp, can we prove this? H is equal to U plus PV. Okay, and then also look at basic enthalpies of some common substances under standard conditions. When does substance have zero enthalpy? It's similar. It's based on reference points. Um, how does enthalpy vary with temperature at constant pressure, with pressure at constant temperature? How does the enthalpy of liquid phase differ from that of the gas phase at saturation condition? How is the latent heat of vaporization related to enthalpy and internal energy change? All right, let's look at all that by opening our enthalpy tab here. All right, first let's look at some enthalpies of different fluids. If you unhide here, you'll see the enthalpy values. Um, what do you see here? You can right away see that the enthalpy is higher than the internal energy, right? Because you have to add the pressure volume work. Okay, all of them you can see enthalpy is a little bit higher than the internal energy. All right, now let's look at the effect of enthalpy. Sorry, let's try to see whether um, U plus PV is indeed true in calculating enthalpy. So here you have different substances: water as a vapor, water as a liquid, R600A liquid, R600 vapor, and different gases. You can calculate the enthalpy uh, in the internal energy um, and the enthalpy, and also calculate their um, specific volume, multiply that with their pressure to get the PV value, then add that with U to create the U plus PV. Now compare U plus PV with H that you calculated directly using props SI. You can see that they match in all scenarios. Okay, it doesn't matter ideal gas, real gas, U plus PV is H because it comes from the definition. All right, so that is true. The next thing to look at is the effect of temperature and pressure on enthalpy, just like we looked at those for internal energy. And you can see it's almost the same. Um, its enthalpy is mainly a function of temperature. It does have an effect from pressure, but like for keeping the temperature different and keeping the temperature constant and varying the pressure, you can see the change in enthalpy is negligible when uh, you look at all these scenarios. So you can say that effect of pressure on enthalpy is negligible. Small effect for real gases. Okay, and clearly there is a big effect of temperature. Okay, why is that though? You know, U plus PV means there is pressure, right? So why is that not a significant effect? Because when pressure increases, V also decreases. Specific volume um, also changes. Okay, so the effect is not that significant. Um, okay, so because you know PV equal to nRT for ideal gases, but for real gases also, when pressure increases, the specific volume decreases for a constant temperature. So even though pressure is increased a lot, there is no effect on U. There's no effect on U on with pressure as we have seen before. But even if pressure is increased a lot, V decreases, so there is no effect of this term. So eventually H behaves similar to U. It has very little effect by pressure. Okay, and H has a significant uh, effect from temperature, as you can see with these numbers here. All right. The next thing to look at is phase change. So in this slide, you can see the how to calculate the phase change using uh, props SI. So you can calculate the enthalpy of vapor phase, enthalpy of liquid phase by choosing Q equal to 1 or 0, and that difference is basically the latent heat. Okay, so it seems like when you compare these fluids, um, so for example water, let's try to compare them in similar temperature ranges. Let's say water is at 10, um, this one would work at 10. So water seems to have very high latent heat compared to some of the common refrigerants. However, we could not use water as a refrigerant because, of course, it doesn't operate really well at low temperatures. It becomes ice really quickly. So that's one of the downsides of water. But otherwise, it seems like it has very good latent heat. Um, so it would remove a lot more heat with a smaller mass compared to other refrigerants. But it's not just the latent heat that you have to worry about to look at cooling. You have to also look at the saturation pressure. So if you look at the pressures for the same temperature, these vapors have very high saturation pressures compared to water. So they vaporize much quickly. So they will remove heat much faster than water because water will take a long time to vaporize if you're just talking about natural evaporative cooling. Okay, so that's another variable that is important, not just the amount of heat that water can remove. How fast that heat can be removed based on partial pressure is also important. All right, now let's look at specific heat capacity. Specific heat is the amount of heat required per unit mass to raise the temperature by 1 degree. Okay, so imagine I have 1 kilogram of water. How much Q or how many joules need to be added to water directly? Assume there is no loss, right? To raise the temperature by 1 degree C. Okay, that's what specific heat is. So it is useful when you're, especially in um, transient studies, to learn how quickly something will heat up. Okay, so if this if this specific heat value, let's note it by C, if this specific heat value C is very high, then it will heat up really slow. Temperature will increase slowly. If the C is low, then the temperature will increase fast. Okay. All right. So if you need only a small amount of Q, it means that the C is low. How's that defined? Um, it's defined for two particular scenarios, for constant volume and constant pressure processes. Okay. Now let's go back to the amount of heat needed for raising its temperature and denoted by Q. But if you go back to the first law of thermodynamics, or the conservation of energy, the Q added, any Q that is added, it goes to change the internal energy, and also part of it goes to do some work, right? And it could be written as this if it is a simple compressible system, and the work can be defined as a simple change in um, volume. Okay, so in such scenarios, let's define the C value for constant V as, and it's defined per mass. This delta change in um, heat per delta change in temperature at constant volume divided per mass. Then you use this inside this equation, this inside this equation, and this is a constant volume process, so this is 0. You get, it's basically a differentiation of internal energy. Okay, you take this mass inside, you get differentiation of specific internal energy. Similarly, Cp can be derived as a differentiation of specific enthalpy. Cp is the specific heat at constant pressure, okay? And the units are joules per kilogram per Kelvin. And we will look into Coolprop on how to derive that. But the next step is, how is the Cp and Cv related to each other? Now, if Cp and Cv, especially for ideal gases, right? Um, you know that H is U plus PV, which is the definition of H. And for ideal gases, PV is nRT. So you can replace H as U plus nRT. Okay. If you divide by mass on both sides and convert to specific values, specific enthalpy is U plus nRT by M. Now, if you differentiate both times with temperature, you get this as a differentiation of temperature, which is in the previous slide, you know that that is Cp, and the other one is Cv. Then you differentiate this with temperature, the temperature is gone, and you have nR over M. N over M, or N is number of moles and M is the mass, gives you 1 over molecular weight. Okay, so Cp minus Cv is R divided by molecular weight. Okay, this is when Cp is in joules per kilogram per Kelvin. If Cp is in joules per mole per Kelvin, or molar Cp, okay, then Cp minus Cv is R. And what is this R? R is the gas constant, universal gas constant, this value. Okay, so when you multiply the molecular weight to Cp minus Cv, you get molar Cp. Okay, if you multiply molecular weight to Cp and molecular weight to Cv, you get everything in joules per moles per Kelvin. In that scenario, if Cp minus Cv is R. If it is in joules per kilogram, then this equation is what results from this analysis. All right. Now let's look at Coolprop one more time and try to answer the following questions. Is Cp really a differential like this? Is Cv really a differential like this? What are some of the common Cp and Cv values? And how do Cp and Cv vary with temperature? Okay, let's go back to the Excel. Let's look at Cp and Cv. All right. Here we've chosen water and air. Okay, one is a closer to a real gas, and the other is more closer to an ideal gas. And one thing I forgot to mention is Cp and Cv are only relevant during single phase. So the phase may be solid, liquid, or a gas. There's no change of phase. So it is when we're talking Cp or Cv, we are either talking about a gas or a vapor or a liquid, but we are not talking about a mixture. Okay, it's defined mainly for single phases. All right, so for this particular case, we have water at this particular pressure and this particular temperature, which makes it a gas at that point, because I've raised the temperature from the saturation temperature by this much. And then what we are doing is finding the same values at a small temperature difference. So you know that if you want to differentiate f of x, is similar to something like this, right? F of x plus delta x minus f of x divided by delta x, where at the limit delta x tending to 0. Same way here, instead of delta x, we have delta t, right? So we are making a very small t as possible with coolprop, and we are finding the difference in internal energy and enthalpy and differentiating them, right? So Cp would basically the difference. Um, Cp is basically the difference of enthalpy divided by the delta temperature, and it's giving us a value. You're also calculating that for this particular temperature and pressure, and both these values match. So that means that this equation is correct for Cp. But if we try to look at what happens to dou U by dou T at constant pressure, whether that will match, it seems like it doesn't really match that well, okay? Because it's 114.79 and this is 1415, okay? So 1415 versus 1417. So it's not a good match, but this, which is what the theory is, seems to work well with coolprop. Same way at constant volume, it seems like CV, which is dou U by dou TV, seems to be matching very well here and here. Okay, as opposed to this value, which is constant volume change in enthalpy, that's not matching well. So the theory works here too. The same thing for air. Okay, so the matching of Cp is fantastic here with the value calculated by coolprop, and the matching of CV is great here also. There is no good matching with Cp here. They're bad because that's not the theory. So the theory works. Okay, so that's partially what we are looking for in Cp and Cv. The other thing was we can compare different fluids here and their Cp and Cv. So we have water, helium, air, nitrogen, and oxygen. And how do we calculate the Cp? Just by using this equation, Cp mass. And for Cv, it's Cv mass and temperature and pressure. And you can calculate for all of these conditions. Water has a good high Cp. Helium seems to have extremely high Cp per mass. You can also convert that per mole by multiplying with molecular weight. Okay, but anyways, here what we have done is we have done Cp minus Cv and multiplied Cp minus Cv with molecular weight. And if you remember, we had looked at earlier that for ideal gas, Cp minus Cv in joules per kilogram times molecular weight is nothing but R, which is 8.314 joules per mole Kelvin. And you can see for some gases that value is really close. So this is closer to an ideal gas, helium. For air, okay, it's not that close, but it is close enough. Okay, and not so much for water at some scenarios. It goes to 8.421. But anyways, so this is another way to check how close to ideal gas you are for any given situation. All right. So that concludes this lecture on the part 1 of thermodynamics principles. We'll have more for you in the next lecture. Thank you.